Hello everybody. In last few sessions we have talked lot about functions. Lot many things you have learnt. Now let me start today something new again in function, hoping that you have already revised your previous things. Let me start with composite function. As name suggests, composite means two or more things are brought together. That is composite. So if two functions f and g are given to me, f is defined from a to b, g is defined from b to c, then their composite GOF is defined as that GOF on x gives me g of fx. Means I will apply g on fx. I hope everybody understood the breaking. I am saying GOF. GOF is the name of the function. That is called GOF as composite function of g and f. Answer would be g applied on fx. And this is to be done for all x in set A. Otherwise function will not be defined. Which function I am talking about? GOF. Now, let us draw it in picture form. Then I think things would be clearer to you. I have shown there ABC. What are ABC? A is domain of f and B is codomain of f. B is domain of g and C is codomain of g. Now, if I take some element x from set A, f would be applied on it. Answer for the outcome would be fx, which I name here as y. And then on this y or fx, I apply g. And I get answer g of y. And what is that y? Y is fx. So, actually what I named in the last set C as z, that is nothing but g of y, and g of y is g of fx. And by definition, g of fx is answer for when GOF is applied on x. That means if GOF is straight away applied on x, my answer would be GOF on x. And that is same as what you get after applying g on fx. Picture looks very simple, definition looks very simple. It looks simple because my domain for function g and codomain for function a, they are same. The thing is, answer for fx what you get, what I am calling here as y, it has to be in domain of g. Then only g of fx is possible. And then only GOF will remain defined. Now here I have taken deliberately domain of G as set B. The reason is that things would be clear to you at least in picture form right away. When we solve more problems, then you may be able to understand that what I said just now, that fx has to be in domain of G. For that you will have to solve questions. Mind you, please, not immediately. As subject proceeds, as you get mature in the subject, maybe little later stage you can try problems on composite of function, but I wanted at least to introduce you what I mean by composite function. Now, simple example I take for whatever I have said just now, that fx is suppose 5x plus 4 and gx is x square. Then how do we find GOF? GOF on x is g of fx. And what is fx? That is 5x plus 4. So in place of fx, I'll write 5x plus 4 and I apply g on it. Now what is g? G does the job of taking square, because whenever g is applied on x, you get answer as x square. So what is g's job? Taking x square of the number on which you apply g. So if I'm applying it on 5x plus 4, my g of 5x plus 4 would be 5x plus 4 whole square. Now since my example has domain, codomain as all set of real numbers only. So at this moment, I can tell you like how we have GOF, I can also have FOG. What would be FOG? FOG applied on x would be f of gx. So I will apply f on x square. What does f do? F does the job that it would multiply 5 to the number and add 4. So I multiply 5 to x square and I add 4. I hope you followed what I said. Also, I have deliberately written both GOF and FOG separately. so that you can see that GOF on X is not same as FOG on X. So order in which functions are applied matters to us. I think that was the crux while taking this example in front of you. Now, I proceed from here and I come to a new part called inverse of a function. Do you remember when I taught something about 1-1 onto function? I mentioned that 1-1 onto function is a bijective function, and bijective function has opened floodgates for some more part in mathematics, and that is nothing but inverse of a function. Inverse of a function is defined only if a function is a bijective. So let us define it. Let f from a to b be a function and it is a bijective function. The condition is f has to be a bijective function. Then inverse of f would be from b to a, like inverse of relation we have done, and it is defined as that x equal to f inverse y if and only if y equal to fx. That means from x to y you reach through f, then y to x you will reach through f inverse. This is what it means. So inverse of a function is defined only when f is a bijective function. Right now at this moment we would know only about inverse function only to this extent. Of course there are a lot of things which you can learn in inverse of function. When we do topic trigonometry, then we will revisit this inverse of a function. So for the time being I cut short here only, and only important points I will try to remember about inverse of a function. Now you all know me. Now every time I try to connect the topic to graph or pictures. So I say graph of y equal to fx and y equal to f inverse x. They are reflections of each other in line y equal to x. Let us see how it is. So suppose y equal to fx I have drawn on the graph, and then I take line y equal to x. Then I take reflection of y equal to fx in the line y equal to x, which I have shown as green color graph. Now y equal to f inverse x is represented by that green color graph. Red curve is for y equal to fx and green curve is for y equal to f inverse x. You can draw both the graphs y equal to fx and y equal to f inverse x on the same set of axes. What you have to do is, one graph or one curve suppose is known to you, you draw that first, draw line y equal to x and take reflection of the known graph, and the reflection would be nothing but the inverse of the function. Okay, the graph of y equal to fx and f inverse x may or may not meet at all. I mean, if you draw on the same set of axes, they may not meet also. But here, what picture I have drawn, they do meet. But where do they meet? They meet on the line y equal to x. So y equal to fx and f inverse x, they may not meet. But if they meet, they have to meet only on the line y equal to x. Also, one more point what you have to remember is that if the graph of y equal to fx is symmetric about the line y equal to x, and if f inverse exists, then fx and f inverse x would be same. Why I say so? The thing is, you can check yourself by drawing a graph which is symmetric about the line y equal to x. And I name the points. I name points A, B, C. Two ends of the curve I am naming as A and C. And the point of intersection of line y equal to x and the graph I am naming as B. What happens? The curve AB, its image would be BC. And the image of BC would be AB. And so, what will happen? The curve which I have drawn for y equal to fx, and even if I draw the curve y equal to f inverse x, they would overlap each other. So, graph of y equal to fx and graph of y equal to f inverse x, they do not differ from each other. They are just the same. So, fx equal to f inverse x. I hope everybody understood what I said. That whenever graph of y equal to fx is symmetric about the line y equal to fx, then, and if f inverse exists, then fx would be same as f inverse x. Mind you, please, this last point we use while solving problems. So it is important for us, and that is why I have given the graphs also, so that you can remember through graph the important point. I think this is good enough for this session. Please stay tuned, keep revising till I meet you again. Thank you.